I am Dr. Basir-Ahamed-Khan, Assistant Professor of Department of Physics, Krishnath College. This is Lecture 3 of Module 6 on Special Theory of Relativity. Today I will discuss these three topics. First one is mass energy equivalence, second is relativistic Doppler effect, and next point is energy momentum relation in special theory of relativity. Now the first point is mass energy equivalence in relativity. This is the mass energy equivalence. To prove the relation, to deduce the relation of mass and energy in special theory of relativity, I consider a force. Let a force F acting along x-axis, and displace a particle through a distance through a distance dx then work done by the force is f into dx. If the velocity of the particle increases from 0 to v, then total work done by the force is total work done by the force is equal to 0 to v integration over 0 to v into fx into f dx. Now this is converted into kinetic energy of the particle Ek. That is, this work done is converted into the kinetic energy of the particle Ek. Therefore, kinetic energy Ek equal to 0 to v f dx. That means 0 to v integration over 0 to v ddt of mv, rate of change of momentum equal to force, and dx. This is equal to 0 to v derivative of mv into dx dt, or this will become 0 to v mdv plus v dm into V. Therefore ek equal to ek equal to 0 to V mv dv mv dv plus v square dm. I just multiply this v into mdv plus vdm. That means it will become ek equal to 0 to integration over 0 to v mv dv plus v square dm. Now I put this equation number 1. Now we have from our previous lecture we know m equal to the relativistic mass m equal to rest mass m0 divided by 1 minus v square by c square. That is, if I simplify this, then I will get m square minus m square v square by c square equal to m0 square. That means, or m square c square minus m square v square equal to m0 square c square. Now differentiating both sides of this equation, differentiating both sides, we get 2m c square dm minus m square into 2v dv minus v square into 2m dm equal to 0, since m0 square c square equal to constant. m0 c square equal to constant. Therefore, from this equation we get mv dv plus v square dm mv dv v square dm equal to c square dm. This is equation 2. So notice here mv dv plus v square dm equal here mv dv plus v square dm. So put equation 2 in equation 1. Then we get ek equal to integration over c square dm, and the range of the integration where v and mass, when v is 0, mass, I just square dm, I just write here to explain the range of the integration. This is velocity and this is mass. When velocity 0, mass is rest mass. When velocity is v, then mass is relativistic mass m. So therefore, from this equation, the range of the integration changes from m0 to m instead of 0 to V. So this is m0 to m. That means it becomes c square into m minus m0, or ek equal to mc square minus m0 c square, mc square minus m0 c square, or mc square equal to m0 c square plus ek. This is mc square equal to m0 c square plus ek. That means we can write this e equal to e0 plus ek, where e equal to mc square, e equal to where e equal to where e equal to where e equal to mc square. This is the famous energy mass relation of Einstein's famous relation of energy and mass, E equal to mc square. This E equal to mc square represents the total energy of the particle. This is total energy of the particle. That therefore I write here E equal to mc square represents total energy of the particle, total energy of the particle, when it is moving with velocity v. When it is moving, it is means the particle moving with velocity v, and E0 equal to m0 c square is the rest energy of the particle, is called the rest energy of the particle. This is called rest energy of the particle, rest energy of the particle, this is the rest energy of the particle. So thus relativistically total energy of the particle moving with velocity v is represented by the E equal to mc square. This is the famous mass energy relation. So relativistically mass and energy are equivalent. That means mass m and energy E are equivalent. Relativistically they are equivalent. And this equation, suppose this is 3. Now this equation 3 is the famous Einstein mass energy relation. Now we give an example of a problem, just an example. Now so that at low speed the relativistic expression for kinetic energy The relativistic expression expression relativistic expression for kinetic energy reduces to for kinetic energy for kinetic energy for kinetic energy reduces to classical relation classical relation classical relation half m0 v square. This is very important. Now if the speed of the particle is low, then this kinetic energy reduces to classical relation half m0 v square. The answer is relativistically kinetic energy of the particle is given by answer. Relativistically kinetic energy Ek, we know that Ek equal to mc square minus m0 c square. The kinetic energy, this is the total energy and this is rest energy. Total energy minus rest energy equal to kinetic energy. So this becomes m equal to m0 divided by 1 minus v square by c square. This is the rest mass, the mass of the particle with velocity v m equal to m0 divided by 1 minus v square by c square, and m0 just this is c square. That means it becomes m0 c square into 1 minus v square by c square whole to the power minus half minus 1. That is, this equation becomes almost equal to m0 c square 1 plus half v by c whole square plus 3 by 8 v by c whole to the power 4 v by c whole to the power 4 plus dot minus 1. This is the binomial expansion. So when the velocity of the particle is small, then we neglect the second and fourth order terms of v by c. Therefore we get when v is very small to c, we neglect fourth order term of higher order terms of v by c then Ek becomes m0 c square into half v by c whole square into half v by c whole square equal to half m0 v square, which is the classical relation of kinetic energy, classical relation of kinetic energy. kinetic energy. Now the Doppler effect. The second point is relativistic Doppler effect. Relativistic Doppler effect. Doppler effect. Relativistic Doppler effect means the Doppler effect of light. We know that the Doppler effect is nothing but the change of frequency due to relative motion between source and observer. If it is sound frequency, then this is Doppler effect of sound. If the frequency is of light, then this is Doppler effect of light. So relativistic Doppler effect is mainly the Doppler effect of light. When the frequency of the light changes apparently due to the relative motion between uh, the light source and observer, light Doppler effect of light appears. That means Doppler effect of light is the apparent frequency change of the light source due to the relative motion between light source and observer. Just I, due to the limitation here, I only put the final result of Doppler effect of light. Suppose here when case 1 when light source and observer coming towards each other coming towards each other then apparent frequency nu equal to nu prime root over of c plus v divided by c minus v, where nu prime is actual frequency of light, and nu equal to apparent frequency of light due to relative motion, and v is the velocity of the frame where light source velocity of the light source. Actually this is the velocity of the light source, or the velocity of the observer towards the light source. So this is equation 1. Second case, case 2, when light source and observer move away, and observer move away from each other, move away from each other, move away from each other, from each other, then apparent frequency nu equal to nu prime, nu equal to nu prime, nu equal to nu prime root over of c minus v divided by c plus v, where nu prime is the actual frequency, and nu is the apparent frequency, nu is the apparent frequency, and v is the velocity of light source, velocity of light source, velocity of light source. And these two, when source and observer coming away towards, move away from each other or move towards each other, then this type of Doppler effect is known as equation 1 and equation 2. Equation 1 and equation 2 is known as longitudinal Doppler effect, longitudinal Doppler effect, longitudinal Doppler effect. This is longitudinal Doppler effect, longitudinal Doppler effect. This is longitudinal Doppler effect. Case 3, when the site, case 3, when the line of sight is at right angles to the velocity of the source and the frequency. When the line of sight is at right angle to the velocity of the source, then the frequency change is called transverse Doppler effect. This is transverse Doppler effect, transverse Doppler effect, transverse Doppler effect. Transverse Doppler effect. Now when the line of sight and the velocity is perpendicular to each other, then this type of Doppler effect is known as transverse Doppler effect. In sound, there is no transverse Doppler effect occurs, but in light source, transverse Doppler effect equal to nu prime root over of 1 minus v square by c square. This is the transverse Doppler effect. Here nu, since v less than c, so therefore since v less than c, therefore root over of 1 minus v square by c square less than 1. That means here nu is always less than nu prime. Apparent frequency is always small than the actual frequency in transverse Doppler effect. But in longitudinal Doppler effect, when source and observer coming towards, move towards each other, move towards each other, the frequency, apparent frequency is greater, apparent frequency is greater than actual frequency. But when the light source and observer move away from each other, then nu less than nu 0, and in transverse Doppler effect, always the apparent frequency is always smaller than the actual frequency. So these three relations arises and gives the relation of apparent frequency of light due to relative motion between source and observer. The last topic is energy momentum relation. The last topic is energy momentum relation. Last topic is energy momentum relation. This is energy momentum relation. The last topic is energy momentum relation. Energy momentum relation in special theory of relativity. Energy momentum relation in special theory of relativity. Energy momentum relation of special theory of relativity. According to relativity, the mass of the particle with velocity v, the mass of the particle of rest mass m0 and with velocity v, mass is m0 root over of 1 minus v square by c square. M is mass of particle with velocity v, and m0 is the rest mass. That means when the mass is in rest, then the mass is m0. Therefore, the momentum of the particle is given by p equal to mv. P equal to mv equal to m0v divided by 1 minus v square by c square, or p square into 1 minus v square by c square equal to m0 square v square, or p square equal to v square into m0 square plus p square by c square. P square equal to v square times m0 square plus p square c square, or v square by c square, that means v square into p square plus m0 square c square divided by c square. That means v square by c square equal to p square divided by p square plus m0 square c square. This is equation 1. V square by c square equal to p square divided by p square plus m0 square m0 square c square. This is equation 1. Now the kinetic energy of the particle is given by relativistic kinetic energy of the particle is given by E minus E0, that means mc square minus m0 c square, or ek plus ek plus m0 c square equal to m0 c square divided by 1 minus v square by c square. 1 minus v square by c square. Then, or ek plus m0 c square whole square equal to m0 square c to the power 4 m0 square c to the power 4 divided by 1 minus v square by c square equal to m0 square c to the power 4 divided by 1 minus p square by p square plus m0 square c square. This is coming from this equation number 1. From equation number 1 we get the values of v square. We put the values of v square by c square into this equation, this equation. Then, or square equal to m0 square c to the power 4 m0 square c to the power 4 into p square plus m0 square c square divided by m0 square c square, right? That means it becomes square equal to c square into p square plus m0 square c square, or square equal to p square c square equal to p square c square plus m0 square c to the power 4. This equation gives the relation between energy and momentum relativistically. So this is, today I know the three things. This is, I know this relation E equal to mc square, E equal to mc square, ek equal to mc square minus m0 c square, kinetic energy, mass kinetic energy relation, and square equal to, this is the energy momentum relation of a particle, relativistic particle. Okay.